So welcome everyone to this webinar to be delivered by Dr. Kaneenika Sinha. Before I introduce the speaker, let me just mention one or two things. The first is that if for any reason your connection is lost in the Zoom app, then you can watch the talk live on Facebook. I'll share the Facebook live stream link in some time. And secondly, please use the chat option to ask any questions that you might have. So if the question is very important, then I'll interrupt the speaker and ask in between. But if it is a bit general, then I'll keep it for the Q&A later on. So without any delay, let me introduce Dr. Sinha. So Dr. Kaneenika Sinha is an associate professor of mathematics at the Indian Institute of Science Education and Research, IISER Pune. She did her PhD at Queen's University, Canada, after which she has held positions at the University of Toronto, University of Alberta, and the Mathematical Sciences Research Institute, MSRI, Berkeley. Then she returned to India and joined IISER Kolkata as an assistant professor. And then she moved to IISER Pune. Her research interests are in analytic number theory and arithmetic statistics of modular forms. Besides being a very excellent research mathematician, she also writes expository articles on number theory as well as her research work. And they have been published in newspapers such as The Hindu, The Indian Express, and many others. So I thank Dr. Sinha for giving us her valuable time. And today she will speak about 102 years of the circle method.
So good afternoon, everyone. Thank you, Manjil, for organizing the Ganitsora seminar and for inviting me to speak in it. Many thanks also to all the audience members who have joined the seminar on a Sunday afternoon. It is an absolute honor that I also just got to interact with Professor Ajit Iqbal Singh long ago when I used to be a student at Lady Shri Ram College. I used to sometimes attend seminars in Delhi University. Some of these were organized for college-going students. And Professor Ajit Iqbal Singh was one of the best speakers I heard. And she's also she may not know it, but she is one of the people who did motivate me, influence me to continue studying mathematics. So on this note, maybe we should start the seminar for today. So you've had a few talks in this seminar on the work of Ramanujan. Today I want to discuss an important number theoretic technique whose genesis goes back to some work of Ramanujan and Hardy, and which was later developed by Hardy and Littlewood after the unfortunate early demise of Ramanujan. This technique is applicable to a variety of what we call additive problems. So let me start with a rough sketch, a very brief sketch of the history of the circle method. So before Ramanujan went to England, he, as we all know, he corresponded with G.H. Hardy. And in one of his earliest letters to Hardy, he mentioned a formula for the partition function, P of n. What is the partition function? It is the number of ways of writing a natural number n as a sum of other smaller natural numbers. Okay, so Hardy and Ramanujan, later once Ramanujan came to England and started working with Hardy around 1918, they developed these ideas in a 1918 paper to obtain an asymptotic expression for P of n. And after Ramanujan's unfortunate demise in 1920, Hardy and Littlewood continued refining and developing this method called the circle method. And most importantly, they used it to study what is called the Waring's problem. So this is to study the number of representations of n as a sum of at most kth powers of positive integers. So k is a fixed integer. Let's say k is equal to 2. So how many ways can you represent n as a sum of squares? If you take k to be equal to 3, in how many ways? First of all, can you actually represent all numbers n as a sum of a bounded number of cubes? And if yes, how many ways are there of doing so? So these are some of the questions which we will state precisely in at least 2 different ways in this talk. And starting in the 1930s, the circle method was widely applied to a variety of additive problems, particularly the Goldbach conjectures. So now I'm not going to talk about these things in linear order. We'll first start with the Goldbach conjecture and use it as a template to understand how additive problems in number theory can be stated. Okay, so at a very basic level, primes, let's start with what are prime numbers. So a prime number is a natural number which is not divisible by any natural number other than 1 and itself. And we all know that any natural number n greater than 1 can be written uniquely as a product of powers of primes. This is called the fundamental theorem of arithmetic. We also know that there are infinitely many primes. Okay, so now the question is it possible, excuse me, is it possible to express any natural number n, however large, as a product of a bounded number of primes? Okay, so let's say, suppose I take any 100 primes and I take very, very high powers. Would these 100 primes be multiplicatively sufficient to build all the natural numbers? And immediately you see that this is not possible. So just one second. Sorry about that. So yeah, so take a finite number C, and then we ask, can we write any n as a product of at most C primes? Now, obviously the answer is no, because you know there are infinitely many prime numbers. So let's take, let's say you take some number C and you write out the first C plus 1 primes, okay, and you take their product. Because of the fundamental theorem of arithmetic, this n does not have any other representation as product of primes. So this tells you that you cannot do this for any finite number C. Now, what we do is we give an additive spin to this question. Now, any n greater than 1 can be written as a sum of prime numbers. Not too difficult to see that, though not necessarily uniquely. So for example, if you have 10, you can write it as 3 plus 7. You can also write it as 3 plus 5 plus 2. And you can write it as 2 plus 2 plus 2 plus 2 plus 2. Okay, so uniqueness is neither true here nor is it needed. So now let's ask, let us take a finite number C. And let's ask, can we write any n greater than 1 as a sum of at most C number of primes? Okay, so this is an additive spin to the previous question, which was a multiplicative question. So this is sort of at the heart of what is called additive number theory. So Goldbach's conjectures are conjectures in this direction. So in a correspondence with Leonhard Euler in 1742, Goldbach made the following conjectures. So first, every even n greater than 2, this was his first conjecture, and it's called the binary conjecture also, the strong conjecture. It still remains open. Every even n greater than 2 is a sum of 2 primes. So any even number, or 4 onwards, can be written as a sum of exactly 2 primes. Now there is another way of writing the same statement, which may seem superfluous to you, but there is a reason why we are restating this. It says that every even n greater than 1, so including n equal to 2, is a sum. 1 is either a prime or it is a sum of 2 primes. Okay, this at most is, we will see how it helps us to generate a very precise mathematical statement, this at most perspective. Okay. Then there is, since there is a strong conjecture, that means there is a weak conjecture lurking around. So the weak conjecture or the ternary conjecture of Goldbach is that every odd n greater than 5 is a sum of 3 primes. Okay, and again, this can be restated in a slightly different way, that every odd n greater than 1, so this includes n equal to 3 and 5 as well, can be written as a sum of at most 3 primes. Right, so 3 and 5 are primes. Okay, so therefore they are a sum of at most 3 primes. Okay. So the strong conjecture, you can see that it immediately implies the weak conjecture, but not vice versa. And to see that the strong conjecture implies the weak one, you observe that any odd n greater than 5, strictly greater than 5, can be written as 3 plus k. And since 3 is odd, the k has to be even since n itself is odd, and k is greater than 2. So if you can write, if you know the strong conjecture that k is a sum of 2 primes, p1 plus p2, that tells you that n is equal to 3 plus p1 plus p2, and therefore it can be written as a sum of 3 primes. So the ternary conjecture, Goldbach conjecture, was proved in 2013 by some very nice work of Harold Helfgott, and we will survey the journey to ternary Goldbach now. So in the 1920s, okay, Hardy and Littlewood proved the ternary Goldbach conjecture for sufficiently large odd values of n greater than or equal to c. So they were not able to prove the Goldbach conjecture, ternary Goldbach, for all n greater than 5. But what they said was for sufficiently large, which they did not quantify, but what they said was that there exists a sufficiently large c such that for any odd n greater than or equal to c, the ternary Goldbach conjecture is true. So now we have to first quantify that c and then go from that c down to our n strictly greater than 5. So the other limitation of their result was that it was under the assumption of the generalized Riemann hypothesis. Okay, so this now in 1937, Vinogradov proved the ternary Goldbach conjecture, again for sufficiently large odd values n greater than or equal to c, without specifying what c is. He did not quantify what c is, but he said that there exists a large enough c such that for all odd n greater than or equal to c, the ternary Goldbach conjecture holds. And he was able to prove this unconditionally. So he did not need the assumption of the generalized Riemann hypothesis. Okay, starting 1956, these methods of Hardy and Littlewood and Vinogradov were refined. And the first step, okay, so the journey to go towards n greater than or equal to 7 is, it has to start with some capital C. And in 1956, Borodskin, actually in his PhD thesis, gave an effectively computable constant. So it's a very, very big number. It's a huge power of 10. But we now know for sure that for n greater than or equal to this huge power of 10, the ternary Goldbach conjecture is true. So now the question is, can we refine the techniques of Borodskin to keep bringing down the values of C? And this is what happened in the journey towards the proof of the ternary Goldbach. So in 1989, Shen and Wong reduced the bound for C to 10 raised to the 43,000. So this is also a huge number, but much smaller than what we had before. And in 1996, they further reduced it to 10 raised to the 7,194, which is also a much smaller power, but still this is a big number. Okay. In 1997, Desuet, Effinger, Theriel, and Zinoviev proved the ternary Goldbach conjecture for all odd numbers n, but the limitation was that their result was conditional on the generalized Riemann hypothesis. So until 2013, the best known unconditional bound was by Liu and Wong, which was 10 raised to the 1346. Now the thing is, one immediate question that comes to mind is that, okay, if your theorem is telling you that something is true for n greater than or equal to this c, can we quickly verify the theorem for all odd n's which is strictly less than this c? Okay, and this requires a lot of computational power. And on the most powerful computers, computer verification of the ternary Goldbach conjecture, which sometimes I may write as 3GC, it can be done up to around 10 raised to the 30. So this is the computational limit that we have so far, 10 raised to the 30. Beyond this, it just becomes computationally unfeasible. And so there is this huge gap between 10 to the 30 and 10 to the 1346, which was unbridged until 2013. And the remarkable achievement of Harold Helfgott in 2013 was that he proved the ternary Goldbach conjecture, proved that it holds for all odd n greater than or equal to 10 raised to the 27. So he brought the power of 10 just a little bit below what could be verified by computers. So combining his theorem and the known computer verification, we end up getting a complete proof of the ternary Goldbach conjecture. Okay, now there are some related developments. So we seem to be emphasizing a lot on writing n as a sum of 3 primes. But what if we wanted to relax this a little bit and write n as a sum of a certain other number of primes? So take a finite number d. Can we write any n greater than 1 as a sum of at most d primes? Okay, take any d of your choice and you can ask a weaker form of Goldbach's question in terms of writing n as a sum of at most d primes. So the answer to this is yes, and this was proved by Schnirelmann. We will be reviewing some of his work shortly. In 1930, again, he says, so his answer is such a d exists. Okay, unlike the multiplicative case scenario, in the additive scenario, such a d does exist and it is effectively computable. So you can find a finite number d such that any n greater than 1 is a sum of at most d primes. But he does not tell us. His result is not strong enough to give us a value of d. But it is a very remarkable development to even know that such a d exists. Okay. In 1995, Ramanujan proved that any even n is a sum of at most 6 primes. And in 2012, Terry Tao proved that any odd n greater than 1 is a sum of at most 5 primes. Okay, so this d can be reduced all the way to 6. Okay, so any n can be written as a sum of at most 6 primes. If it is odd, it can be written as a sum of at most 5 primes, and if it is even, then at most 6 primes. So we have come very close to the bounds of Goldbach, the conjectures of Goldbach, but we are not quite there yet before Harold Helfgott's work. Now, a remarkable fact is all of the above results that we've stated so far use the circle method. And as I just mentioned, I'm going to be a bit repetitive about this fact, that the origin of the circle method lies in a 1918 paper of Ramanujan and Hardy. Okay. So now, this before we address this technique particularly, let us just expand our horizons a little and talk about what really additive number theory is, what lies at the basis of questions that are considered in the domain of additive number theory. Okay? So let us take S to be a subset of the natural numbers, in any subset that you like. For example, so far we had the set of primes, but if you don't like prime numbers, you could take S to be a subset of, say, squares, or you could take S to be S to be the set of all squares of natural numbers, or you could take S to be the set of any kth powers, okay, say k equal to 3 or k equal to 4 and so on. So now the question is S additively sufficient to build the complete set of natural numbers? Secondly, is there a finite C so that any natural number, however large, is a sum of at most C elements of S. So we are just generalizing Goldbach's questions to a bigger class of subsets of natural numbers. So as I mentioned, let's take S to be equal to x squared, where x is any natural number greater than or equal to 1. And Lagrange showed in 1770, so those of you who are taking a course in number theory in college, this is typically what is proved in a first course in number theory. Any natural number n can be written as a sum of at most 4 squares. So in this case, your C is equal to 4. And this 4 is quite sharp because there are numbers which cannot be written as a sum of 3 squares, for example. Around the same time, Edward Waring made the following conjecture. And we have to be very careful with the wording of this conjecture. It says, every n greater than or equal to 1 can be written as a sum of 4 squares, 9 cubes, 19 fourth powers, and so on. So what he's indicating is that if you take S to be the set of any set of kth powers for a fixed natural number k, then you can, that set is additively sufficient to build the entire set of natural numbers. And you can also find a finite C so that any natural number can be written as a sum of at most C many elements of that set of kth powers. And when he says and so on, this is what he means. So the question is this true for any arbitrary kth power? And also, if it is there some kind of a formula? So given, say, if you're talking about cubes, you are saying that there are at most 9 numbers of cubes needed to build all the natural numbers. Similarly, for fourth powers, that number is 19th. So for k, is there some formula for such a number, g of k? So this is Waring's problem. And the reason the circle method is often named after Hardy and Littlewood is because they applied this method, which goes back to the work of Hardy and Ramanujan, to address Waring's problem. And they wrote they wrote multiple papers from 1920 to 1928 in which they completely solved Waring's problem. Okay, now before looking at a solution of Waring's problem, we have to learn how to state it in a more precise way. So we are going to learn 2 different ways of doing it. So since we mentioned Schnirelmann, let's look at his way of stating these type of additive problems. So this uses a notion of density, which is very different from the natural density notion. So let us take A to be a subset of the natural numbers. Okay, and for any little n greater than or equal to 1, let capital A of n denote all those numbers in capital A which are bounded above by n. So the natural density of A is defined, this is something we know well, as the ratio of A of n over n as the limit n goes to infinity. And if this limit goes to 0, we say that this A has 0 density in the set of natural numbers. The Schnirelmann density is a little bit different. So you use the same ratio A of n over n, but now instead of looking at the limit for large values of n, you look at the infimum over all the numbers n greater than or equal to 1. So the Schnirelmann density is sensitive, unlike the natural density, it is sensitive to small values of n. So for example, let's take a very, very simple set E and O, which denote the set of even and odd numbers respectively. So it won't take you very long to quickly see that the natural density of both of these sets is half. In fact, O of n, if you write out the number of odd numbers up till n, it is exactly 1 by 2 if n is even, and it is n plus 1 by 2n. So in simpler forms, it is half plus 1 by 2n if n is odd. So either way, O of n is at least a half, and for several values, it is half. So this tells us that the Schnirelmann density of O is equal to half. So for the odd numbers, the Schnirelmann and the natural densities match. But for the set of even numbers, that does not happen. The Schnirelmann density of the set of even numbers is 0. Because this is sensitive to smaller values of n and e of 1, there are no even natural numbers less than or equal to 1. So e of 1 is equal to 0. So the Schnirelmann density of the set of even numbers is 0. In general, note that if 1 is not an element of a set A, then A of 1 is 0, and therefore this would imply that the Schnirelmann density is 0. Okay. Now, Schnirelmann also defined in a very nice way the notion of sums of sets. So take two such subsets, A and B, of the natural numbers. And now what we do is we define the sum set of A and B as the set of all possible x plus y, where x and y are either, so x and y are respectively in A or B, but they could also take values 0. Okay, so x is in A union 0 and y is in B union 0. So in particular, for example, if you take A to be the set of primes, then the sum set of A with itself consists of 0, all primes P1, and all possible sums P1 plus P2. Okay, and what we now do is m times A, for any natural number m, we define m times A to be the sum set of A with itself m many times intersected with the natural numbers. Okay, so in the set m times A, we don't take the element 0, for example. So a typical additive problem asks you, if for your favorite set A, can you find some number m so that m times A is equal to n? Okay, maybe I can pause for a few seconds in case anyone has a question up to now. We could.
So we have some questions, but these are sort of like general questions, not.
Okay, so I'll assume that people are following the notation. Okay, so like I said, so there's a very short way of expressing a problem, which in English takes a lot of words and sentences, is m times A equal to n for some m, so for some fixed natural number m. Schnirelmann's theorem is a very remarkable theorem which says that it relates this question to his notion of density and says that yes, if the Schnirelmann density of a set A is positive, then the answer to the above question is yes. Okay. However, if delta of A is equal to 0, then we don't know what happens. So for example, let us take k to be greater than or equal to 2, and let b sub k denote the set of all kth powers of natural numbers. It will not take you very long to check that the Schnirelmann density of b sub k is equal to 0. Okay, but so we cannot apply Schnirelmann's theorem to solve Waring's problem. But in 1943, Linnick showed the following theorem. Well, the Schnirelmann density of b sub k may be 0, but you can find some positive integer m, so that m times bk would have positive Schnirelmann density. And once you do that, then you can apply Schnirelmann's theorem to m times bk rather than just bk. So therefore, as a consequence of this, there exists a natural number g1, okay, such that, and when I say g1 of k, it means it depends on k, such that g1 times the set MBK is the set of all n. And I leave it as an exercise for you to check that G1 times MBK is equal to G1 times M of B sub K. Okay, so you are giving me now a positive number, finite number, G1 times M, so that G1 times M of BK gives us the entire set of natural numbers, thanks to Linux theorem. Okay, so then the question is, what kind of bounds can we give to these values G1M? Okay, so Hardy and Littlewood show that if G is something greater than 2 to the K, then every sufficiently large n can be written as a sum of at most G number of kth powers. Note here that for many values of K, through other methods, one could find other smaller values of G. Okay, but Hardy-Littlewood theorem says that 2 raised to the K plus 1 is large enough to build the entire set of natural numbers. Not entire, but sufficiently large. More about this, more precise formulation of this coming soon. Okay, now let's go back again to the Goldbach conjecture. Let P be the set of primes. Schnirelmann showed that there exists a natural number D such that D times P is equal to the set of all those natural numbers which are greater than 1. Ramanujan showed that 6 times P is equal to the set of all even numbers. And Terry-Tau's theorem can be restated as that any odd number, so the set of all odd numbers greater than 1 is exactly equal to 5 times P. And the weak Goldbach conjecture in this language says that, well, not 5, actually 3 times P is sufficient to generate all the odd numbers greater than 1. And the strong Goldbach conjecture says, well, you don't need 6, 2 times P is equal to E. Okay. Okay, now we move to another formulation of these additive problems using what is the main topic of this talk, namely the circle method. So this also starts with a very elementary observation. For a real number x, particularly you can take x to lie between 0 and 1, you define E of x. So this is an important notation. We are going to keep using it throughout the talk. So please remember that E of x denotes e raised to the 2 pi I x. So which is a complex number given by cosine 2 pi x plus I sine 2 pi x. And from this it is immediate that E of x is a periodic function of period 1. That's why it is enough for us to consider E of x in the interval 0 to 1, in any interval of length 1 actually. Now the circle methods originates in a very trivial and a very easy integral identity, which says the following. If you integrate, take any integer m and integrate E of mx dx from 0 to 1, if m is equal to 0, you get 1, but for any non-zero integer, you get 0. Okay, so in some sense, what this is telling you is this integral, the left-hand side, gives you a fancy way of writing 1. Okay, in the case when m is equal to 0. So now, how do we apply this trivial identity? And just one remark: if you look at when you integrate this function, complex valued function, from 0 to 1, okay, if you make a suitable change of variables, you will see that you are actually integrating a complex valued function on the unit circle centered at 0. So this is actually where the word circle method comes from. Let us now take a natural number n and define the exponential sum f of x to be equal to sum of all the E of px, where p runs over all the primes up till n. Okay, so we are taking some n, fixing it, and we are denoting f. So this f depends on your choice of n. So if you want, you can write it as f sub n. We will try not to clutter the notation too much. So f of x is the sum of the, this exponential sum, which is coming from the sums E of px, where you run over all the primes less than or equal to n. Now from this, suppose I want to take the square of f of x. Okay, so it immediately using the fact that e of p1x times e of p2x is e of p1 plus p2 times x, we are able to write out this expression for f sub 2 of x. Okay, not f sub 2, sorry, f square of x. So this is the sum of all such e of nx, mx, where m is a sum of two primes, p1 and p2 less than or equal to n. Okay, now what we do is we take this function f square of x, combine it with e of minus nx, where n was something that we'd chosen before, and integrate this function. Integral from 0 to 1, f square of x times e of minus nx dx. Okay, it turns out to be equal to, you've got the integral 0 to 1 times this sum here, okay, of e of p1 plus p2 of x. By an immediate interchange of integral and sums, we end up getting summation. So we take the sums over p1 and p2 outside, and then inside the integral, we've got e of p1 plus p2 minus n of x dx. And you just saw by your elementary integral identity that this inner sum, this inner integral is 1 exactly when p1 plus p2 is equal to n, and it is 0 otherwise. Okay, so this f square of e of minus nx dx is actually measuring for you the number of primes p1 and p2 up till n, such that p1 plus p2 is exactly equal to n. Okay, so here is this counting expression on the right hand side, which you are able to write as an analytic expression, which involves evaluating integral of certain appropriate exponential functions. So now the question is, if you want to check whether an even n or a sufficiently large even n can be written as a sum of two primes, what you really need to show is whether this right hand side is something greater than 0. And therefore, in the language of the integral, can we show that the integral of this function, f square of x e of minus nx dx, is greater than 0, either for all even n or at least for some sufficiently large even n. Okay. So to address the binary Goldbach conjecture, therefore, to summarize again, our object of interest now becomes this integral from 0 to 1 of f square of x e of minus nx dx, where, to remember, f of x is this exponential sum which is coming from all the primes up to n. So now we need to understand how to evaluate this integral. In a similar way, to address the ternary Goldbach conjecture, we repeat the same process, but this time instead of f square of x, we need to take f cube of x, and n is some odd number. Okay. In between, there is the intermediate question: does there exist a positive number d such that the integral of f of x raised to the d times e of minus nx dx is positive, at least for sufficiently large n? And Schnirelmann's question, answer to this question is yes, you can find such a positive number d. Okay. So let's just look at the theorems about sums of primes in this new language. So Vinogradov, so what Vinogradov showed, and we will actually discuss briefly a proof of this theorem, that for sufficiently large odd values of n, this integral associated to the ternary Goldbach conjecture is positive, which is really what you need to show. Okay? And Helfgott's theorem makes Vinogradov's theorem effective. It says for all odd values, it doesn't use this wishy-washy, I mean, I shouldn't say wishy-washy, but whatever. It doesn't just say some sufficiently large odd value. It says very precisely for all odd values of n greater than or equal to 10 to the 27, this integral is positive. And combining this with computer verification up to 10 raised to the 27, the ternary Goldbach conjecture is proved. So the method that Harold Helfgott uses first relates to reducing the ternary Goldbach behind the circle method. Okay, so now some key steps in the circle.
Sorry to interrupt.
Sorry, yeah.
Could you repeat the last sentence again? Your connection was lost.
Okay, so what I was saying was that Vinogradov shows that this integral is positive for sufficiently large odd values of n. And what Helfgott does is make that formulation more precise. He says for any odd n greater than or equal to 10 to the 27, this integral associated to the ternary Goldbach is positive. And so the ternary Goldbach conjecture holds for all n greater than or equal to 10 to the 27. But what about values of n less than 10 to the 27? There you use computer verification, which has already been done. Okay, so it has already been verified that the ternary Goldbach conjecture is true for all n less than 10 raised to the 27. So combining this computer verification with Helfgott's effective version of Vinogradov's theorem, we get the ternary Goldbach conjecture. Okay. So the key steps in the circle method are as follows. So the first thing that we really need to understand, since we have to integrate square or cube of this function f of x, we want to understand what are the points on the unit circle, what are those values of x, where this function takes very, very high values or where it peaks in comparison to other points of the unit circle. So the most fundamental observation is that this function, this exponential sum f of x, peaks at rational numbers of the form a by q, where q are suitably bounded. We will make this a bit clearer in a few minutes. So what we really need to do is we have to take the interval 0 to 1 and we partition it into two parts. The first part is where the function is expected to take very, very high values. And the other part is where it will take relatively smaller values. So the part where you expect it to take very high values, they are called the major arcs. So what are major arcs? They are unions of very tiny intervals around the rational numbers at which the function peaks. And the minor arcs are simply the what remains when you remove the major arcs from the unit interval 0 to 1. So now let us take, in order to determine what the major arcs are, first let us just focus on certain rational numbers and see how you would actually evaluate the value f of x. So now for values like 0 of 1, these are very easy. Since e of p times 0 and e of p times 1, they are both exactly equal to 1. So f of 0 and f of 1 both just capture pi of n, which is the number of primes less than or equal to n. So nothing, so this for 0 and 1, the evaluation is immediate. Now let us complicate it a little bit. So let's take f of a half. Okay, so now you've got the sum over p less than or equal to n, e raised to the 2 pi I p over 2. So this is e to the I times pi p. Okay, now we all know that e raised to the I pi is just minus 1. So we have summation of minus 1 raised to the p as p runs over all the primes up till n. Okay, other than p equal to 2, this number will always take the value minus 1. Okay, so you have 2 minus pi of n minus 1. So essentially what you get is some number which is close enough to minus pi of n. Okay, so in absolute values, this is giving you pi of n. So the size of f of half is again close, sorry, I meant to say pi of little n. Now f of 1/3, let's calculate that. Okay, so now what we notice is that if you write p, so you are interested in evaluating e of p over 3. Okay, and because of the periodicity of the exponential function, what you know is that this value simply depends on the residue class of P mod 3. So if P can be written as 3 times L plus R, where R is 0 or 1 or 2, okay, then E of P over 3 is exactly equal to E of L over 3. We also note here that since P is a prime, R cannot be equal to 0. So the 0 residue class will not be considered. Otherwise, P will cease to be a prime number. Okay, so now with this in mind, what we do is, like I said, it really matters. All that matters is the residue class of P. So we first separate all the non-trivial or the non-zero residue classes, mod 3. So R goes from 1 to 2, E of R over 3. We can just bring that out since E of P by 3 is equal to E of R over 3. And in the inner sum is the sum of all those primes up to n, which are congruent to R mod 3. Okay, now there is a very famous theorem in number theory of Siegel and Wolfish, which tells you that irrespective of your choice of residue class, any fixed residue class will have the same number of primes up to n. Okay, and this is given approximately by pi of n over phi of 3. Phi of 3 here denotes the Euler phi function, which is the number of co-prime residue classes to 3. So since 3 is a prime, that's the only co-prime residue classes are 1 and 2. So this is basically approximately equal to minus pi of n over 2. And now when I say approximately, what does this mean? I'm to keep our work not too technical in this presentation, I'm avoiding long expressions. So what this approximation sign means is that this sum is equal to minus pi of n over phi of 3 plus something which we call an error term, which would be of order or smaller than pi of n. Now, from the prime number theorem that pi of n is asymptotic to n over log n. Okay, so when I say approximately, it means this is equal to this number plus something which is of order smaller than n over log n. Okay, so let's now generalize this to values at rational points. So in general, if you take any q greater than or equal to 1, and if you have a prime which is congruent to R mod q, then since R is a prime, P is a prime, it forces your residue class R to be co-prime to Q. Okay, so just as we did it for f of 1 by 3, we now generalize this immediately to f of 1 by q, where q need not necessarily be a prime number. Okay, any number q. So f of 1 by q can be written as the sum E of P over Q, okay, where your P runs over all the primes up till n. Again, we classify terms of this sum into appropriate residue classes mod Q. So the outer sum is all those R mod Q which are co-prime to Q, E of R over Q. And in the inner sum, for every such residue class, you also have to count the number of primes up till n which are congruent to R mod Q. Okay, so as again by an application of the Siegel-Wolfish theorem, this is approximately equal to pi of n over phi of q. The inner sum is approximately pi of n over phi of q times this sum E of R over Q, where you run over all the co-prime residue classes mod Q. And again, I leave it as an exercise for students to verify that this inner exponential sum actually turns out to be equal to mu of Q, where mu is the Mobius function. If Q is a square free number, mu of Q takes the values -1 or 1, depending on whether Q has odd number or even number of prime factors. And if Q is not square free, then mu of Q is equal to 0. Okay. So the same thing can be generalized to any, we were so far taking all rational numbers with numerator 1, but even for any any numerator a, as long as a is co-prime to q, which is okay with us because we will write our rational numbers in the lowest possible form. So a and q are co-prime to each other. So by repeating the previous calculation again, what you have is that f of a over q is near about pi of n times mu of q over phi of q, where phi is, as I mentioned, the number of co-prime residue classes up to q. Now we make a nice observation here. As q goes to infinity, phi of q also goes to infinity, and therefore the size of f of a over q goes to 0 as q goes to infinity. So when we are talking about contribution of f of x at various rational numbers, what this is telling us is that this function will contribute more at those rational numbers a over q, where q is a small denominator. Okay. Now, we were making claims about function attaining peaks at rational numbers. How do we know that, or how do we determine that? So to do this, what we have to do is, and by the way, all of this actually, I'm really doing some hand waving, precise, writing all these formulas precisely, very technical, and they take some effort, but they will needlessly confuse us during the presentation. So I'm keeping things simple here. We compare, what we do is, let's compare the average size of f of x. You see, on the unit interval 0 to 1, there are lots of rational numbers and there are lots of irrational numbers. Okay, so we know how to evaluate the function at rational points, but what do we do at irrational points, for example? How can we at least understand the size of the function? So to do that, what we do is, we talk about the average size of the function f on the unit interval. Okay, so when we say average size, so now since we are just interested in size, so we take the absolute value of f of x, okay, integrate it from 0 to 1, okay, and divide it by the length of the interval 0 to 1, which is just 1. So this expression here gives us the average size of f of x. Okay. Now f of x is a complex number, and we all know that it's not all that easy to play with absolute values of complex numbers. These are square roots of certain quantities, so we play a cheap trick. We take, well, how about simplifying this problem by looking at squares of the average size? And if we know something about the square of the average size, perhaps from that we can deduce what the average size is. So now we've got this integral of absolute of f of x square dx. So these kind of identities are used very frequently in analytic number theory. So this is square of the absolute value, which we write as f of x times its complex conjugate. All right. So now you've got the integral 0 to 1, and you've got a double sum here. So sum over all the primes e of p1x, and again sum over all the primes, but now you have e of minus p2 of x because you were taking the complex conjugate. Okay. And so now again we bring the summation out and take the integral inside. So you are summing over all the prime pairs p1 and p2 of the integral of over 0 to 1 of e of p1x minus p2 of x dx. Again, by our trivial integral identity, we know that this takes the value 1 exactly when p1 is equal to p2. And for p1 not equal to p2, this will just be 0. So it captures only those pairs in the sum where p1 is equal to p2. And so this you end up getting just pi of n. So the average size of the square of f of x is around, it can be well approximated by pi of n. So what do we have? So therefore from this, of course, like I said, I'm just writing it in a very easy way. All this has to be formulated very, very clearly and very precisely. It makes the treatment technical. So the average size of f of x is approximately the square root of pi of n. Okay, whereas from what we did before, we have seen that the value at a rational point where the denominator is not very big is somewhat close to pi of n. Okay, so from this, what we do is, so this tells us that, see, pi of n is much, much bigger than square root of pi of n. Okay, so those rational points where the function is taking the values close to pi of n would be contributing unusually high values of the function to this expression. So what we now do is, we take the major arcs of 0 of 1 to consist of a union of very short intervals centered around these rational numbers a by q, where q is bounded above by some suitable bound which depends on your little n. So just, you don't have to worry too much about the technicalities here. All we are doing is, we are partitioning our unit interval into the major arcs and the minor arcs, where major arcs are unions of very, very short intervals or short windows around a by q, where q is not something very big. It is suitably bounded. And minor arcs are things that are left behind. Okay. So now what we do is, we write our, just a little observation though, if you are taking a to be, so we are going over, so if you take, for example, a by q to be equal to 1, then the interval is not, the interval ends at 1, but you take, so something of the form 1 minus 1 over f of n comma 1. Okay, so at the end points of the unit interval, you have to be a little careful. For anything inside the unit, strictly inside the unit interval, you can take these short windows that go both sides of that rational number. So we now write the integral. Remember, this integral from 0 to 1 is what we have to evaluate. We want to find out whether it is positive or not. So we write this as a sum of the integral, corresponding integral over the major arcs, plus the corresponding integral over the minor arcs. So the integral, once you start doing the calculations, the integral over the major arcs gives us the main term. As we had seen before, that f of x is very large at these points and in these windows, but the length of the arcs are very, very small. On the other hand, when you are removing very, very tiny windows from the unit interval 0 to 1, what you are left behind is practically the entire interval 0 to 1. So the length of that is quite big, but the values of the function f of x in this leftover portion are very small. So this is the balancing act that we do between the major and the minor arcs. So evaluation of the integral over minor arcs is a very intense calculation, and it uses cutting edge techniques from very deep techniques in analytic number theory. So from the theory of exponential sums and Diophantine approximation theory. I will just leave this here. I won't go into all these details right now. So let us just focus on the minor arcs. Let's again just have like a rough philosophical understanding. So for the binary Goldbach conjecture, our minor arcs, so the integral you have to consider is f of x square e of minus nx dx over the minor arc. And you play a very trivial bound for this is, so I did not make many comments about the integral of this function over the major arcs, but with some calculation, you can see that it is roughly to the order of pi of n. Okay. And now when you want to know what happens for the minor arcs, so if you try the trivial things, like the most trivial thing that you can try is just bring the absolute value inside the integral. Okay. And the disadvantage of this is that you lose a lot of cancellations that could have otherwise happened. Okay. And in fact, this is really bad because, so first of all, you get rid of e of minus nx since the absolute value is just 1. So you have integral absolute f of x square dx, which is less than or equal to integral over the entire interval 0 to 1. This minor arcs were pretty much the entire unit interval. Okay, so a rough upper bound for the integral over a very trivial upper bound is pi of n, which does not give us anything because it is nearly as large as the main term. We would like to have some savings over pi of n for this computation to be effective, to be useful. So now we play another trick. Okay, we take the absolute of f square of x. Again, we bring the absolute value inside. Okay, but now we break this integral into two parts. So we take one power of absolute value outside and take the maximum value over all the minor arcs. And we would hope that since now we are running over the minor arcs where the function does not take unusually high values, this number might turn out to be fairly small. Okay, but how small? And how small do you want it to be? And the inner one is just the integral over absolute f of x dx, which by our previous rough calculation is something to the order of square root of pi of n. Okay, so what we need is, just to go back, what we want to do is we want to be able to show that this quantity at the bottom is much smaller, of an order smaller than pi of n. What we know is that the average value here is square root of pi of n. Okay, so we would like to have a bound for the maximum value of absolute of f to be much smaller than square root of pi of n for this method to work. But what that means is, what you're trying to basically do is, you require this, somehow this method is so restrictive for us that we end up requiring the maximum value of a function to be of smaller order than the average size. Not happening, right? How can the maximum value be of smaller order than the average size? So this is the reason why the circle method, in the way that we are working on it here, fails for the binary Goldbach conjecture. Binary Goldbach is still an open problem. So for ternary Goldbach conjecture, this demerit, this limitation disappears. Okay, so what we have is, remember, we had cube of f of x. So again, now we can take maximum of absolute f of x. And then in the inner integral, we've got, for the major arcs, we do it by various techniques and it's not too hard. For the minor arcs, now you've taken maximum of absolute of f outside, and inside you've got absolute of f squared of x over the minor arcs. Okay, and this again, this integral was something that we had calculated that it was of the order of pi of n. In fact, it was exactly equal to pi of n. So this is less than or equal to maximum of all those, maximum of the absolute of f as x runs over all the minor arc, all the elements in the minor arc, times pi of n. Okay, and now here we know enough about the value of the functions at the minor arcs to be able to get an upper bound for the integral over the minor arcs, which would be of appropriately smaller order than the integral of the major arcs. Okay, so all that now it has to be, the technical calculations are more involved. So Manjal, I see somebody raised hand. Is this somebody has a question?
So we have some questions, but
not related. Okay, we can wait, is it?
Yes, yes.
Okay, so let's continue. Okay, so this was very, very, just to give you a general idea about the method. Now we write this theorem, Vinogradov's theorem in its more technical form. It says that there exists, okay, so let n be some odd number n, so some odd positive integer. there exists an arithmetic function, g of n, which lies between positive constants a and b for sufficiently large odd values of n, and the quantity that you were looking for, the integral of f cube of x times e of minus nx dx, which turns out to be equal to the number of ways of writing n as a sum of 3 primes, okay, can be written as this g of n times n square over 2 plus O of, by O I mean that this quantity here, again, it is a long formula, but at the end of it, you get something which is bounded above by some constant multiple of n square over log n raised to the c. So what you are doing here is you are saving a factor of log n over the main term. Main term is something of the form n square times g of n, which you told me is a constant between a and b. Okay, so the error term is saving a factor of log n to the c. It appears as if it is saving a very little factor, very small quantity, but even that is useful for us. So this is Vinogradov's theorem basically. So how does it tell us what we were claiming it tells us? So what this theorem tells you is basically that there exists some constant, positive constant r, so that this integral is greater than or equal to g of n square by 2 minus r times n square over log n raised to the c, where c is something greater than 0. So if you want to show that this integral is positive, it would be enough for you to show that the right hand side is positive. So to have this to be positive, you can cancel off n square, and it is sufficient for us to show, since g of n lies between a and b, it would be sufficient for us to show that a over 2 minus r over log n to the c is greater than 0. In other words, with appropriate simplifications, what this theorem is, Vinogradov tells us, is that if you are very careful with all your calculations and you keep track of all the constants and all the constants and the orders that show up in the error terms, then you will have a nice lower bound, explicit lower bound for n, such that for any n greater than this lower bound, you can write, for any odd n, you can write that n as a sum of 3 primes. Okay, so now the question is, when Vinogradov worked on the proof of his theorem, was he able to make all of these precise? And the other question is, even if these can be made precise in Vinogradov's work, is this bound small enough so that you can combine it with the known computer verifications and just deduce all of ternary Goldbach? Okay, so actually the answer is no. So this just gives you a very rough, very large upper bound. And I'd already mentioned to you the journey of how you kept tinkering and kept reducing the lower bound. So basically, so another way to understand Helfgott's theorem is that he makes Vinogradov's theorem effective enough to give us the ternary Goldbach problem. Okay, so I've already, sorry for being so repetitive about it, but this is a fact, unfortunately, that gets overlooked a lot. The roots of the circle method lie in a 1918 paper of Hardy and Ramanujan, which is titled Asymptotic Formulae in Combinatory Analysis. This paper is also available online, so if you would like to go and have a look at it, please feel free to do so. So in this paper, they were interested in deriving an asymptotic expression for the partition function, which is the number of ways of writing n as a sum of positive integers up to n. P of n, in related, so not exactly at that time, but a few years later, P of n was also studied by Rademacher, who made very significant contributions to the work that Hardy and Ramanujan had initiated. So the roots of the work of Hardy and Ramanujan further go back to one of the earlier letters that Ramanujan had written to Hardy from India, in which he had written an expression for P of n, which later turned out to be incorrect, but it did indicate that he had some intuition about the circle method. Okay. Now, just to understand the genesis, how Hardy and Ramanujan, what version of the circle method they address. So now what we do is, as before, let us consider a subset of natural numbers, okay? And for two natural fixed numbers, g and n, let RAG of n be defined as the number of ways of writing n as a sum of at most g number of elements from A. So a more precise way of saying is, it is the number of I either lies in A or takes the value 0 such that the sum is equal to n. To understand this, so they consider the sum P of Z. So just like we considered the exponential sum, okay, E of, in the Goldbach's conjecture, it was E of Px as P runs up till n. So here we are not necessarily restricted to the set of prime numbers. We have a general subset A, okay, and now this A could have infinitely many elements. So they write out this generating function. It need not be a finite sum any longer. They take all possible power z to the A, where A lies in A. And then if this sum, okay, if this has a radius of convergence greater than 1, then inside the domain of convergence, we observe that P of z raised to the power of g can be written as a sum. Okay, so if you take this whole sum and raise it to the power g and do appropriate interchanges of summation, what you end up getting is P of z raised to the g can be written out as a power series expression, okay, around z equal to 0, where the coefficients are these representation numbers that we are after. Okay, and those of you who are studying complex analysis know that by Cauchy's theorem, and if you have not studied complex analysis, don't worry, you have already seen this integral in a different form using our exponential functions. But by Cauchy's theorem, you have another alternative way of expressing this RAG of n. And so now you need to understand, and since the radius of convergence of absolute of P of z, was absolute of z less than 1, what we need to do is we need to take a closed contour. Okay, so I made a typo here. I want to take something to be of radius which is strictly less than 1, not equal to 1. And a change of variables. Okay, now, had we been lucky, had this series converged outside, so if this were also valid for the unit circle, then we could make a change of variables, z equal to E of x, and rewrite our AG of n in the form that we are familiar with. But this is different from the way we had written stuff before, because here f of x is an infinite sum. Whereas what we did was, it was a very clever observation by Vinogradov, that when you are writing out this expression P of z to be equal to z to the a, you don't really have to consider all possible a's. You can take a bounded above by something that depends on n, since you are starting with a specific n. Okay, so all these convergence issues then vanish. And we end up getting a similar, an expression which is very similar to what we had for the problems of Goldbach. Okay, so a very brief overview. So you've got this P of z as it appears in the paper of Hardy and Ramanujan. You've got this generating function P of z, which is being generated by these partition numbers P of n. The series converges when absolute of z is less than 1. So inside this region, if you have a closed circle which is centered at 0 and with radius less than 1, P of n is exactly equal to this integral here. Okay, now we know that for absolute of z less than 1, P of Z can also be written as this infinite product. Okay, and this reveals a lot of things, useful things to us. So suppose you wanted to do this integration over the contour C. Okay, so notice your Z to the n plus 1 in the denominator will not create any problem, because it is approaching, absolute of Z is approaching 1. It is going away from 0. So we are safe here. With P of Z raised to the G, however, what you will end up getting is, so you've got powers of this infinite product, which has 1 minus Z to the n in the denominator. So obviously, if Z to the n comes closer and closer to 1, this function is going to become problematic. It's just going to explode. In other words, as we approach any nth root of unity, there is a problem. So these are the problems where we had seen in a different way that your generating function, your function takes peak values at rational numbers. So we make the same observation here using a different formulation, that this integral takes large values as Z approaches any root of unity. That is, Z approaches complex numbers of the form E of A over Q, where A by Q is any rational number with A less than Q, A less than or equal to Q. Okay. Now, I'm not going, this is a very, very involved calculation, but this is just to give you sort of a rough introduction so that you can by yourself go and read the existing literature. So going back to the expression of P of n, we make a suitable change of variables. And this time we actually end up integrating not from 0 to 1, but from I to I plus 1 of the same expression that we had before. Okay. So if you want to integrate and you've got this function which is analytic in the upper half plane, okay, so we end up breaking down this contour into a more complicated contour, which I'll show you in a second. But after doing all that work, one can derive an asymptotic. Okay, so as n goes to infinity, P of n is asymptotic to this function. Okay, so now the question is how do we tackle this contour integral? Okay, so this, I've taken this picture from the Wikipedia page on the Hardy-Littlewood circle method. The Wikipedia page calls it, which is unfortunate. I think it should be called the Ramanujan Hardy-Littlewood circle method. But this picture is also what the picture that Manjul shared when he sent out the announcement for my talk. So what is happening here? You need to just 1 second. Yeah, you have to integrate a function. Okay, between on the contour. So on the straight line between I and I plus 1, because the function is analytic in the upper half plane, we are able to convert this contour from I to I plus 1 into a different contour that goes from I to I plus 1 in a different way. So first what we do is there are these forged circles, which are circles on the upper half plane, which are tangential at rational points. Okay, so 0 and 1 are rational points with denominator 1, 0 over 1 and 1 over 1. Okay, and these you have to define these circles in such a way that their radius is appropriate enough so that any two forged circles will either not intersect each other, or they will intersect each other at exactly 1 point. Okay, and what are these rational numbers? You write out these rational numbers in a certain order. So first you write those numbers which have denominator 1, so 0 over 1 and 1 over 1. Then you write those rational numbers which have denominator 2. Okay, so 1 over 2 and 2 over 2, which is already there. And remember, we are taking A over Q, where A and Q are co-prime. So now when you take 1 by 3, Okay, so you have a circle which is touching 1 by 3. You have another circle which is touching 2 by 3. Okay, then you move on to those rational numbers which have denominator 4. So now you have 1 by 4. Okay, 2 by 4 is already there, 1 by 2. You don't have to write it again. And then the next one is 3 by 4. Okay, and similarly, as you keep increasing the size of the denominator, you have more and more circles. Okay, so the first, when you want to change the contour, first at the first stage of bounded denominator 1, what you do is you start at I and go all the way till that point where this circle is touching the circle which corresponding to the rational number 1 over 1. Okay, and then at that point, it just shifts to the other contour and goes back to I plus 1. Okay, next stage is if you want to look at all those numbers with denominator bounded up to 2. So now you go from I, you follow this contour of the big circle all the way till you hit the fourth circle corresponding to half. Then from there you travel on this smaller fourth circle and go on till the point where you hit the big fourth circle corresponding to 1 again, and then you move back again all the way till I plus 1. Then if you want to keep doing this procedure at different stages, the next stage is 1/3. So again, now you go from I all the way till the point where this circle meets 1/3, the circle at 1/3. Then you travel on this circle, go to the circle corresponding to half, travel on the circle corresponding to half, go till you reach the one at 2/3, then travel on the smaller circle to reach the rightmost circle, and then go back again to I plus 1. So you can keep drawing these contours for each level n, and then you've got to evaluate that contour integral on these more complicated things, which are essentially in disguise. Those are the contours which we had talked about in terms of evaluating over the major arcs. Okay, so this is just a more complex analytic way of stating that method. So this is the origin of the circle method as found in the paper of Hardy and Ramanujan. So in the last couple of minutes, I just want to make some quick remarks about Waring's problem, which was the foundation on which the circle method was first developed by Hardy and Littlewood. So here what we have is, we've got our problem is to express. So k is something greater than or equal to 2, and we want to express any number n as a sum of kth powers. And what we do is we write out all the g tuples x1 up till x sub g, where xi is either a natural number or it is 0, so that the sum of the kth powers of these xi's give us n. Okay. So by including 0, what we are saying is we are trying to write n, we are trying to find out in how many ways n can be written as the sum of at most g numbers of kth powers, as opposed to exactly g numbers of kth powers. So obviously, each x sub I definitely has to be less than or equal to n raised to the 1 by k. And so just as we had an expression, an exponential sum involving primes, now we have an exponential sum involving kth powers, e of m to the k times x, where m runs over all the numbers starting at 0, since now we have this at most issue, going all the way till n to the 1 by k. Okay, and we do the evaluation again. So now, since we are interested in writing n as a sum of g many, at most g many powers of k, so we take f of x and raise it to the g. Okay, and then take the corresponding e of minus nx dx. This will only capture those values where x1 plus x1 to the k plus x2 to the k and so on till xg to the k is exactly equal to n by the same elementary integral identity that we had seen before. And so we have now stated this problem in a language very similar to that of the binary and ternary Goldbach conjecture. And in a series of articles written between 1920 and 1928, Hardy and Littlewood applied the circle method and completely took care of Waring's problem. So here is a more precise formulation of their theorem in the spirit of the theorem of Vinogradov that we wrote down a while ago. So let k be greater than or equal to 2, some power k which you fix, and let g be greater than or equal to 2 to the k plus 1. Okay. Then there exists some delta so that rgk of n, which is that integral that we just wrote on the previous page in equation 1. Okay, so that integral can be written as a main term, okay, of the order of n raised to the g by k minus 1 plus an error term which is of the order of n to the g by k minus 1 minus something small. You can find, so all you're saying is you can have an error term which is a little bit smaller than the main term and write out your expression for rgk of n. And your g of n, by the way, we know it to be, so gamma, of course, it denotes the gamma function that we are all familiar with. And g of n is an arithmetic function, which, as in the case of Vinogradov's theorem, it is a positive function. And for all n greater than or equal to 1, it has absolute bounds, absolute positive bounds in both directions, a and b. So basically this g of n, you can basically treat it like a constant. Okay, it is not adding anything to the order n to the g by k minus 1. So the main term is of the order n to the g by k minus 1, and you have an error term which is smaller. And therefore, again, just as we did in the remarks after Vinogradov's theorem, using this, we can deduce that for n sufficiently large, you can write for sufficiently large values of n, this rgk of n would be positive. Okay. So this is pretty much all that I had to say about the circle method today. So just to briefly summarize, today we looked at the circle method applied to the Goldbach problems, the partition function, and Waring's problem. Okay, so now some resources for those of you who would like to do further reading about this. So first is this very nice book, An Invitation to Modern Number Theory by Stephen Miller and Ramin Taklubigash. This has appeared in this one of these red books, you know, the Trim series brought out by the Hindustan Book Agency. So this is like a problem book. Actually, it covers many important areas of modern number theory, like a lot of research work now is going into the direction of probabilistic methods, connections with random matrices, and of course, the latest developments in circle method. So this book covers all of that, and it covers that in a problem format. So they give you a philosophical introduction to the concepts, and they make you work out the details, and they've presented the problems in a very systematic way. So just like Ramanujan started his study with Carr's synopsis of pure and applied mathematics, for you, this book would be a good candidate to work on and learn learn important parts of modern number theory. The other book is Additive Number Theory, the Classical Basis. So this is one of these Springer graduate texts in mathematics. It's written by M.B. Nathanson. So it's a very well-written book where he gives a very careful treatment of Waring's problem, of the ternary Goldbach conjecture, and he explains how the earliest treatments of the subject were done, like how Vinogradov proved an ineffective form of ternary Goldbach, for example. So this would be a good book to read. And this is very different from the previous reference. They give all the details. So if you like to have everything in front of you and work through that, this would be a great source. Then if you want to study the circle method as applied to the partition function, there is this another Springer GTM book, Topics in Analytic Number Theory by Hans Rademacher. And Harold Helfgott has not only uploaded complete proofs, the complete papers containing his proof, he has also written a nice monograph on the ternary Goldbach problem, where he develops all the basic analysis and number theory techniques that are needed to prove the theorem that he proved. And he gives this, and this is available for you on archive. You search ternary Goldbach problem, you will get it. Okay. There's two video resources I wanted to refer you to. So first is the Hardy-Ramanujan formula for the partition function. So you must have seen I was very wishy-washy while talking about the partition function. So Professor D. Surya Ramana has given a very nice and detailed lecture on this formula. So if you go to the YouTube channel of Institute of Mathematical Sciences, Chennai, you will be able to get access to this lecture. Okay, the final reference I wanted to refer to was this lecture by Stephen Miller, one of the authors of the first book that I mentioned. So Stephen Miller has his own YouTube channel, and his lecture is Dr. Seuss and the Circle Method. Now, I don't know about you people. I certainly did not know about who Dr. Seuss was. Apparently, he's a famous American author of children books. Perhaps the younger members of the audience may have read his books. So but there is some character in his book, this cat in a hat, where there's a cat who wears a very peculiar type of a hat. And so he actually, Stephen Miller, dresses up if you like some drama. So if you want to learn circle method in a nice dramatic way, I refer you to this lecture. He dresses up like this cat out of a hat. And there is also some famous poem of Dr. Seuss, I think it's called Sneetch. So he just rewrites Sneetch. He makes modifications for it to be relevant to the circle method. So this would be a good lecture for you to attend. So I'll stop at this note.
Thank you so much, Madam, for the very nice and very nice introduction to the circle method. Also very detailed and so many problems are discussed. So before moving on to the Q&A session, we have a special short section on Professor R.P. Bambah today. He was supposed to attend the webinar, but due to some personal reasons, he could not attend. But we have with us Professor Hanskil and Professor Khanduja with us. So I would like to ask them to speak something about Professor Bambah, but before that, let me very quickly mention some things about Professor Bambah. So he, of course, needs no introduction, but I'll try to give a very brief summary of his life and works. I mean, even though this task is impossible in such a short time, but I'll still try. Professor Bambah was born on 30 September 1925 in Jammu. So he's going to celebrate his 95th birthday very soon, and we would like to wish him on that very special occasion from all of us at Conjecture. He did his schooling in Wazirabad and Sialkot, now in Pakistan, after which he joined Government College Lahore, where he did his degrees up to masters. It should be mentioned that during his masters, he scored 600 out of 600 marks, which has remained unbeaten. That means nobody could ever do it again. So he was 1 year senior to the Nobel laureate Professor Abdul Salam, with whom he maintained a lifelong friendship. So after his masters, Professor Bambah, he started his research work under Professor Sarvadaman Chawla, who is another very well-known number theorist from India. And he, after doing some research with Professor Chawla, he left Lahore in February of 1947 and joined the University of Delhi. But he left Delhi in 1948 to go to the University of Cambridge, where he worked with Professor Louis Mordell for his PhD, which was awarded in 1950. Then Professor Bambah had several positions. So he started out as a reader in Punjab University in 1952, but then he left to join the Institute for Advanced Studies in the US for 2 years. He eventually became a professor at Punjab University in 1958, but left for a short period to join as a professor in the Ohio State University in USA. He came back to India, and later on he became the Vice Chancellor of Punjab University in 1985. So he has been decorated with numerous awards. So some of them are that he was awarded the DSc degree by the University of Cambridge. He is a fellow of the Indian Academy of Sciences, the National Academy of Sciences, and the World Academy of Sciences. And very significantly, he was awarded the Padma Bhushan Award in 1988 by the government of India. Professor Bambah, he not only worked in number theory, geometry of numbers, and discrete geometry, but he also established a tremendous school at Punjab University, which worked and settled some of the outstanding problems under his guidance and collaboration. And probably Professor Hanskill and Professor Khanduja would say something about this. So as I mentioned already, he's turning 95 very soon. And on behalf of Ganit-Sora, I wish him good health in the years to come so that he can keep guiding us. And now let me ask Professor Hanskill to say a few words. So she's also a very well-known number theorist from India. And if Professor Hanskill could unmute and say a few words. So I can see Professor Hanskill is in the call.
It's muted.
Yes, so let me try to unmute her. I think there is some issue with Professor Hanskill. If Professor Khanduja would like to take over. Professor Khanduja, can you hear me?
Yes.
Hello, ma'am.
Would you like to take over? Professor Hanskill seems to have some problem with the audio.
Okay, let me first of all compliment and congratulate Kaneenika Sinha for a very good lecture.
Thank you.
And you also for going on with this series so successfully, choosing very good speakers. Actually, my association with Professor Bambah goes back to 1971 when I joined MSc in the Department of Mathematics, Punjab University, Chandigarh. And but I will and over these years we have been in close contact as student, as a MSc student, then as a PhD student, then as a teacher in the department. He was head, I was a teacher in the department, and then finally this is a very long connection. And I will just talk about my last meeting with him. That was on 24th August last month, 1 month back. I had written he taught me algebraic number theory while I was in the first year of PhD. He was supposed to teach it to MSc students, but MSc class was small and I was doing PhD at that time and I had not studied algebraic number theory. So I took up his course as pre-PhD course. Of course, all the books will tell he was a devoted teacher, he was a good researcher, all the awards you mentioned. But one thing I remember, he was a national professor at that year. He never missed a class. If he had to go to Delhi for some meeting, he will always take an extra class. So we had complete 6 hours a week with him. And I liked his subject so much, the subject he taught, that I took up this as a topic of my research, but with somebody else, not with Professor Bambah, because he was traveling here and there. He was going out of India, so I joined it with Professor Luther, but learned it from him. And now in the COVID days, when I and my husband were away from each other, he was in US, I was in Chandigarh. So I wrote I wrote a textbook in algebraic number theory. Whatever he taught us, I also taught it many times to the students. Same thing, but of course, I had some additional knowledge, additional this thing from my guide, Professor Luther. So I wrote a book and I completed it. And before submitting it to Springer, I wanted to give a copy of it to Professor Bambah. So on 24th August, I went to his house to give him a copy of the book. And then he told me that his first student, Gurnam Kaur, from Punjab University, first PhD student, wrote her PhD thesis in 1964, and she worked on the problem of minimum discriminant of algebraic number field of totally real fields of degree 6. And I was shocked when he told me that the smallest cubic field of signature 1 1. Signature 1 1 means that one real isomorphism and one pair of complex isomorphisms. So means it's not totally real 3-degree field. The minimum discriminant absolute value of the minimum is 23, and it is attained by such a field q theta, where theta satisfies this polynomial. I was shocked. He has stopped teaching for the last 20 years. Last 40 years, he's not teaching. He's not guiding formally a PhD student for the last 40 years. And still, and then he said, for totally real cubic fields, the minimum discriminant is 49. And he immediately blurted out, oof, I was shocked. And then he said for 6-degree fields, he's said 2 things, and I was ashamed that I taught it only a few years back and I have forgotten. Of course, these are now mentioned in my book. For a few days I will remember, but not for 40 years to come. So he is just extraordinary. He has an extraordinary interest in mathematics, extraordinary interest in life, extraordinary warmth in his heart. Whenever I visit him, he always asks about my family members, my sons, my daughter-in-laws, my grandsons. Where are they these days? What are they doing these days? And of course, he also asks about my husband if he doesn't accompany me. So with these words, I will, because I have a lot to say. I know him so much as a student. He has changed my life completely. One more incident I would like to quote. When I got married in the year December 1979, and immediately after 1 year I had a kid, and there was no research. Only I was doing teaching work, not writing any research paper, not guiding any student. And Professor Bambah was the vice chancellor at the time, as you mentioned that he became the vice chancellor in September 1984. He became the vice chancellor of Punjab University. And a vice chancellor of Punjab University is always a member of the governing body of PGI, Postgraduate Institute of Medical Education and Research, where my husband was an assistant professor at that time. So he told me, Sudesh, one day he took us to tea, all the research students and junior staff. He took us to a canteen tea, where we used to sit on the ground with our cross-legged. He used to sit with us on the ground cross-legged. So he told me, see, your husband has written 4 papers in 1 year, and during the last 4 or 5 years or 4 years, you have not written a single paper. I said, yes. I said, yes, I have not written. But I don't know how many husband has written. He says, yes, I looked at the report of PGI, annual report of PGI, and there were 5 papers by Dr. Khanduja. So from that day onwards, I said, I must spend time on research. I must adjust my time between my family and research. And from that day onwards, there was no looking back. So it was he who awakened me from his sleep. There are many other instances when he was vice chancellor at Punjab University, and the whole of University Grants Commission was finding a financial crunch, and he sent a notice to every faculty member that we should arrange our own funds, we should apply for a project. And at that time, I did not know, I was just a lecturer, I didn't know how to write a project. how to write problems. So I wrote a project just with my hands. At that time there were no computers. Typing was just handwritten typing. So I just wrote it, a project, CSIR project. I remember I took it to his house because I could not go to the vice chancellor's office. He was very busy, and I took it to his house. He didn't have time to read, so he passed it on to another person called Professor Shankar. They suggested me some modifications, and I submitted the project. And after that, I was always having a project. When one project was about to finish, I used to submit another. So that way, he changed the lives of others. He changed the lives of students. He played a very positive role. With these words, I think I should end my speech, because it's a Sunday afternoon and everybody has family duties. So I will end my speech with this.
Thank you so much, Professor Khanduja. I forgot to mention, so Professor Khanduja is also a INSA senior scientist at IISER Mohali. And I have shared an article that she and Professor Hansgill has written about Professor Bambah in the chat box. You can take a look at it if you are interested to know more about Professor Bambah. Now I'd like to ask Professor Hansgill. I see that she is available in the call now. If she would like to say a few words. Sorry, Professor Hansgill, you were on mute. Could you click the unmute button? Let me try. So can you see the button which says unmute at the bottom left of your device? I'm clicking from here, but it is not working from my side. So I'm not sure why it is not working, Professor Hansgill.
Change whatever situation is there.
Sorry, Professor Singh?
You ask her to change the situation because it comes unmute. So you say you change whatever is there on the left hand side button.
Yes, so as you can hear, Professor Hansgill, if you just click the button which says unmute, it should work. Okay, it seems to be not working because I can also do it from my end, but when I click
you do it.
No, it is not working from my end also. I click on it, but it does not respond.
So maybe, she's already on the right button, so she shouldn't change it. Maybe Sudesh can call her.
No, I'm at a great distance from her.
I will call her.
Okay, so maybe Professor Singh can call Professor Hansgill. In the meantime, we can take up one or two questions.
Yes, you can take up questions. I will call her. Okay.
Okay. So we have actually many questions. I'll try to select some of the ones which have direct connection. So one of them is that other than the problems that you showed, are there any other areas where circle method can be applied?
Yes, so one area that I did not go into much is additive combinatorics. So this is a new and very happening area of mathematics. The origin lies in the circle method. And there's a wide variety of questions which combine number theory and combinatorics in a nice way, where circle method can have good applications.
So probably I should have asked this during the talk, but what is the generalized Riemann hypothesis?
Okay, so the Riemann hypothesis, as you know, is a statement about the non-trivial zeros of the Riemann zeta function. Now, just like the Riemann zeta function, there are a class of generalized zeta functions. These are called Dirichlet L functions. So now these are not.
Okay, this is Professor Singh.
Yeah. So
Yes.
instead of summation 1 over n to the s, now what you do is you take a Dirichlet character chi mod n. Mod some modulus, and write out summation chi of n over n to the s. Okay, so these can also be studied analytically, just like the Riemann zeta function. And the generalized Riemann hypothesis is the assertion that the non-trivial zeros of these Dirichlet L functions also lie on the critical line. So in our calculation that we went over, the general Riemann hypothesis comes, the full force of the GRH comes into play when we talk about the error terms in our calculation. Remember, I used the symbol approximately. So the function value is approximately something. So it's equal to that quantity plus an error term. Now, how sharp the error term is depends on the GRH.
Okay. So in one of the slides, you showed the intersection of A plus and so on, m copies of A and n. Why is n taken and not any other set, or can any other set be taken and studied some questions related to that?
Yeah, you can take any subset of natural numbers. For example, even we ended up restricting ourselves to the set of odd numbers or the set of even numbers. So yeah, you could take any subset of n and study.
Okay. So this is not really related to your talk, but I'll still ask, and it's up to you if you wish to answer it. Is there any instant iterative formula to calculate the non-trivial zeros of the Riemann zeta function?
I'm to be honest, I'm not an expert in this at all, so maybe it's better I don't answer this.
Okay. So in Schnirelmann's result, what does effectively computable mean?
So what effectively computable means is that if you can quantify the main term and the error term appropriately, so instead of just writing the expression as a main term plus O of something, if you can write out what that O constant depends on, okay, then your result will actually give you a lower bound C, so that for all n greater than or equal to C, n can be written as a sum of whatever, either sum of certain number of primes or a certain number of kth powers. So Schnirelmann's theorem tells us that first of all, you can find such a C. Okay, and then the next step is, well, how do you find that C? There you have to look at your asymptotic expression carefully and study the error terms there. Yeah.
So is it possible to establish a general formula to find consecutive primes?
General formula for consecutive primes. I'm not aware of. You mean using the circle method, or?
Yeah, probably yes. I mean, it's not.
Okay, I don't know.
Okay.
The idea of consecutive primes is very, very interesting. Like if you want to study spacings between consecutive primes and compare this to other probabilistic models, this is a very deep and fruitful area of research. But not really relevant to our talk, I think.
So in the slide that you showed for the circle method for PN, one question that came at the time was that does the ordering matter for the XIs that you showed?
XIs.
Yes. So I think you had.
So yeah, because we are writing them as tuples, right? So yeah, but I mean, in the way that we are counting RGK of n, so what happens is that if you have 1 to the k plus 2 to the k plus 3 to the k, or you write 2 to the k plus 1 to the k plus 3 to the k, or 3 to the k plus 2 to the k plus 1 to the k, they all get counted separately in the way we have formulated the problem. So yeah, there the ordering matters.
This is another general question. So what are the basic applications of number theory in real life?
So one of the most flashy and very useful applications is, of course, cryptography. So how do you transfer information from your computer to the server of your bank when you're trying to enter your credit card number? That actually uses techniques from number theory. Okay? So it depends on the fact that if you have a very large number n with, let's say, 500 digits, okay, and you know that it is a product of two primes, that's all you know about it. But given such a number n, it is for now, I mean, if the n is large enough with our current computational powers, we cannot decompose it into its factors. And this lies at the heart of the safety of your internet transactions. So sorry for bringing this up, but since this question has been asked, I wrote an article for Bhavana magazine on prime numbers, and I also described applications of prime numbers in that article. So it's available on my website, and Bhavana, of course, is available online. So I encourage the person who asked this question to read this article to have a better understanding.
So I am sharing the article in the chat box if somebody wishes to take a look at it.
Yeah, thank you.
So another question which is probably a bit removed from the talk is that, I mean, is the work of the Polymath project and Yitang Zhang related to the circle method, or is it something completely different?
It is not related to the circle method, but it does ask questions about primes. So the fundamental question is, are there infinitely many twin primes, right? So are there infinitely many pairs of primes of the form p comma p plus 2? Okay. So what Yitang Zhang showed was that, again, in spirit, it is similar to the kind of statements we were making. So there is an effectively computable upper bound. In fact, that upper bound is at most 70 million. So that there are infinitely many pairs of primes of distance 70 million between, at most 70 million between them. So it sort of gives an effective upper bound. And the journey to the twin prime conjecture is to go down from 70 million down to 2, bring that bound down to 2, that there are infinitely many pairs of primes with distance 2 between them. Okay, so this whole polymath project, and it refines the methods of Yitang Zhang to first, I think they have already, the state of the art right now is a 3-digit number, like 246. So there are infinitely many pairs of primes with distance at most 246 between them. And so Yitang Zhang's work does not use circle method. I think he uses sieve methods, not in his work.
So there is a question that I got now. How promising can probabilistic approaches be considered to solve number theory problems and derive bounds?
So what a probabilistic approach does is it helps you to predict what could happen. So suppose you have a question and you don't know which way, you cannot make any accurate predictions. What probabilistic number theory does for you is it teaches you how to view the quantity that you are studying as, let's say as a random variable. And and then come up with the guesses based on how a bunch of random variables behave. Sorry, this is a very, very rough answer, not deep, but probabilistic approach is one of the most important modern approaches to number theory. But more than giving you, I feel that more than giving you an explicit answer, it gives you a framework within which to search for an answer.
So I have been told that Professor Hansgill will send an audio to Professor Singh and then I can play it out. So until I get that, do you mind answering a few more questions?
Yeah, sure. Yeah, I hope people are not getting bored.
A follow-up question to the just answered question was that may you prescribe any book on probabilistic number theory? Which was asked by...
Yeah, so in fact, this book by Stephen Miller and Ramin Taklu-Bigash, it has an entire section devoted to probabilistic methods in number theory. And that is a good source to learn it from. I'm learning it myself. It's new for me also. And this is the source that I'm learning it from.
So one question that I received, but I did not ask, now I can ask, is why was Ramanujan's name not associated with the circle method?
Actually, I don't think it was deliberate. So as I understand the history, in this 1918 paper, there was some form of the circle method that was used, but Ramanujan passed away in 1920, and the method was very explicitly and very carefully developed in subsequent papers of Hardy and Littlewood. Okay, so for example, this bunch of papers they wrote in the 1920s on the Waring's problem. So because of that, the name has somehow been associated, and one of the earliest books on the circle method, which I did not refer to, but it is actually a good book. It's a book by R.C. Vaughan, and he ends up giving it the title Hardy-Littlewood circle method, and so the name has stuck. But I don't think it is a deliberate attempt to sideline anyone. It's just that unfortunately Ramanujan was not around when this method that he had an intuition about was developed over a period of time.
So I have got the audio now. If I can just play it and we can listen to it. So this is from Professor Hansgill. Unfortunately, we could not have her live on the meeting because of the audio issue, but she has sent me a message via WhatsApp and I'll just play it now.
This is the message that I want to be read at this.
So is this audible?
Yeah.
Okay.
I can hear it.
Okay.
Okay. First of all, I would like to congratulate the organizers for organizing this wonderful talk. And I would like to congratulate Dr. Sinha for this very, very nice, very clearly done and explained talk. And I am very glad that I could attend it. I'm grateful to Professor Ajit Iqbal Singh for informing me about this. And actually, it is Professor Bambah who made it possible for us to meet, because he invited Ajit from Delhi to Chandigarh to visit our department or stay as long as she wanted in our department. And she stayed for a couple of years. And since then, we have had very valuable interaction. And I have a very good fortune of being Professor Bambah's PhD student. We were a group of 5 students at that time. And out of those, 4 did PhD with Professor Bambah and 1 with Professor Hansraj Gupta. Gurnam Kaur, that Dr. Sudesh mentioned, she did her PhD on the topic she explained, but other 3 of us did in geometry of numbers. He built a school in Chandigarh. His students, 2 of us, myself, Vishwa Chandra Dumir, had joined, and then later now he has some grand student, Dr. Madhuraka is there, Dr. Grover is there, and he had Dr. Taram Singh. So with these people around, we could work with all of us together, worked in some very hard problems in geometry of numbers, particularly the non-homogeneous minima of quadratic forms. There was a conjecture of Watson, which we together made efforts, and we could prove it along with the known results, and also obtained the corresponding results on the positive minima. And more recently, we have, with the particular efforts of Dr. Madhuraka and her student Litika, proved some results about a very famous conjecture on the non-homogeneous or product of linear forms. So it is all due to the advice and encouragement of Professor Bambah. Even although he's retired, he is not actively doing mathematics, but he is always ready to discuss mathematics and discuss the problems whenever we meet. We'll talk about mathematical problems, some problems, old problems or new problems. And as Sudesh had said, that he has such a remarkable memory. And he's like a walking encyclopedia in the problems that he is interested in. For example, I talked to him about this lecture on circle method. And then also there is a recent conjecture of Keller that we talked recently, just yesterday. And then he could recall all the results that were proved, like when he was active on these. He told me he had lectured in our department in about, I think it was to be 1963, on circle method. And he remembered all the history and he remembered the method. He explained to me, within a few minutes, all the ideas behind it, the major arcs, then the minor arcs, etc. And then about Keller's conjecture, he explained to me the history. It's really remarkable. And it's so energizing to talk to him. Though sometimes he feels that actually he's not doing something much in the last few years, but still his mind is very active. And he has such an understanding of the background, of the motivation. He can exactly explain to you the reasons why things are done the way they have been done by mathematicians in the problems that he is interested in. And he has very wide interest. So he has done much about mathematics and about the university. He is still a member of the Senate, and he attends various other meetings or functions still, even though health is not great, but he has got good health. And I would like to take this opportunity to wish him good health in the coming years, and hope that we can continue our mathematical interactions for years to come. Thank you very much for inviting me to talk about this. Thank you.
that was the message I received from Professor Hanskill. So on that note, I would like to bring the session to an end. And wish Professor Bambah good health, and also thank Professor Khanduja and Professor Hanskill for saying some nice things about Professor Bambah. And also thank you to Kaneenika ma'am for giving such a nice talk and for answering so many questions. And yeah, so with that, I would like to end the live stream and also stop the recording. So thank you so much.